Thank you so much for the kind introduction, and thank you very much for having me in this one of the world's largest maritime conferences. It is my honor to share my view with you today. I changed a little bit at the last minute to my slides, so if you need the new slides, let me get your email and I will send you the new slides. Today I'm going to talk about three things. First, nuclear power is rising. Second, many registers in the world are defining the safety requirements for nuclear power. Third, many registers or classification organizations are dominating SMR technologies. As you know, back in July, IMO announced Net Zero 2050, which will be a historic milestone that has brought a lot of changes. In 2019, as you heard from Clarkson Research, LNG-fueled ships will help us reduce CO2 emission by 50% by 2050. That was our prediction, but everything has changed since the announcement from the IMO. New builds should be 100% eco-friendly ships, and you heard alternative fuels today, including ethanol, methanol, hydrogen, and ammonia. And now we have to add nuclear power to the list. Nuclear power ship is called new ships. Many are interested in them because SMR's safety is increasing, and when SMR is used for ships, it can offer economic feasibility and it can enhance speed. And safety codes are under development, and we will see a number of safer SMRs in the future. According to UNCLOS Article 23, bilateral and trilateral agreements between and among countries around the world are increasing, so it is opening up a new era for nuclear ships. And ship owners are also paying their attention to the current trend. If you look at the picture, the y-axis represents CAPEX and OPEX, and x-axis represents operation. And green fuel will be 2 to 3 times more expensive than existing fuels, but SMR fuel ships compared to diesel and LNG will be up to 5 times cheaper. That is why we are calling SMR-fueled ships the next generation new ships. If you look at the right-hand side, y-axis represents dollar costing for hydrogen production, 1 kilogram of hydrogen production. So solar power will cost 5 times more than nuclear power in terms of production. So nuclear power is emerging as a new fuel because it is safer and it is cheaper. So you may ask why SMRs are safer. I'm going to answer the question based on this plot of Professor Hyung-Chul Bang. X represents micro and y-axis represents output. The The power is increasing, as you can see in this graph, and it is divided by multi-core. Every single element here will not be burned, even without external stimulation. Let's apply the same logic to large nuclear power plants. It is exposed to the risk of melting down, but if it gets smaller, I mean, if it is a SMR, without the risk of a meltdown, we can create power at a cheaper price. Now we are seeing MicroURANUS. It offers 5 times less output compared to SMR, and it doesn't present any risks of meltdown or radioactivity. So this might offer a promising solution to the shipping industry. IMA and OECD recently announced a certain aspect of SMR. According to their announcement, there are about 100 projects under development, and 20 out of them can be applied to the shipbuilding and shipping industries, and they can be divided into 4 types broadly. One is PWR. It requires water, and China, Russia, and Korea are leaders here. Second is salt. It is called MSR, molten salt reactor. If you enrich uranium, you can create a nuclear power. And the US is adding chloride here. And Denmark is adding fluoride. And the US and the Netherlands are leading this area. The third is LFR. Sweden, Russia, Italy, the UK, and Korea are developing this part. The last one is sodium fast reactor. It is related to heat pipe reactor. It is in the form of heat pipe reactor. It is under development in the US for application in the maritime industry. These 4 types of new fuel have their own safety requirements. Professor Kodaris offered analysis on the safety requirements of these 4 types, and he said most of the accidents in the nuclear power industry can be defined as nuclear submarines and oil tankers. And oil tankers are directly related to chemical explosion. So today, I'd like to tell you how we can define these requirements for these 4 types of nuclear power. First, nuclear explosion in the nuclear power industry. Maybe some of you saw this movie Oppenheimer. Let's take a look at the picture on the right. Uranium enrichment ratio is represented by x-axis, and y-axis represents criticality. And this blue line is criticality graph. The higher the criticality is, the higher the possibility that nuclear explosion will happen. And military-grade nuclear submarines are fueled by HBU. The critical mass here is only dozens of kilograms. So if nuclear materials are placed in the submarine body, nuclear explosion could happen. And for commercial ships, only less than 20% of uranium enrichment can be used. If it goes over that threshold, the critical mass will be about 400 kilograms, and that can be installed or mounted on a rocket, and it cannot be used for any military attacks or operational attacks. So we are talking about LEU. 5% of enriched uranium is used, and the fourth generation of nuclear power plant is using molten sodium reactor, MSR, and it is somewhere between 20% and 50% of enriched uranium. In the past, Russia operated nuclear submarines fueled by enriched uranium, and those submarines were refueled at seas, and nuclear materials were approached by the body when the ship body is shaken or moved or unsettled by waves that could increase the risk of explosion. That is why Russia shifted its position and decided to refuel their nuclear submarines on ground and onshore. The U.S. is using 90% of enriched uranium, and nuclear submarines of the U.S. fueled by nuclear power, its life expectancy or life cycle is longer than the conventional submarines. But for icebreaker, more than 20% of enriched uranium cannot be used. That is why Russia brought their submarines to a dry harbor, a dry deck, because they decided that for commercial ships, that number is not high enough. As you can see here, highly enriched uranium, it offers more than 40 years of life cycle, and criticality is almost 1. But when you use 5% of enrichment, nuclear fuel should be replaced every 2 years. If you use 20%, the refueling cycle goes up to 20 years. So SMR is too dangerous to be used in the maritime industry, and it can also generate too much waste. That is why SMR is not that popular. In contrast, the blue dots here, they represent fast reactor. They burn uranium at 280 degrees. And that supplement plutonium-239. So the intensity of the flame can last at the same level for as long as 40 years. So it can offer more promising solution to the maritime industry because you don't have to refuel or replace your nuclear fuel for up to 40 years. So most of the research focus has been on fast reactor in recent years. A fast reactor includes MSR and liquid FR, and gas FR was found to be safe, but it is too big according to some people. So I'd like to elaborate on that. So today I'm going to focus on MSR and LFR. MSR was developed by TerraPower, founded by Bill Gates, and Core Power, UK organization, is using that for maritime industry in building ships. It is important to note that chemical explosion and nuclear explosion cannot be ruled out as a possibility. I'm going to show you a short video.
Total surprise. I was expecting a little bit of splattering, but what I got was like a full-on powerful explosion. look at the cavitation bubbles on the glass, and it just shattered it and blew that fish tank glass across my yard.
여기 보시다시피 빌 게이츠
The Bill Gates group is using MSR, but it offers a risk of chemical explosion. And MSR is not likely to be cooled down naturally. So let's assume that there is an accident. You have to manually cool down MSR. But so when it is mounted on a ship, it could cause a sloshing effect when there is a sea motion. So you always have to consider there is a possibility or a risk of explosion. Next is heat pipe reactors. This is called sodium fast reactor, SFR. Let me show you another video. As you know, sodium, when it reacts with water, it could cause a chemical explosion. Could you click the play button here? So sodium fast reactor also carries a risk of chemical explosions. So when there is a volume in SFR, it could lead to a nuclear explosion. So aren't they too dangerous? Einstein left this important, famous quote. He said, people and human beings tend to repeat their mistakes, the same mistakes. So the answer lies here. So there has been a review of fast reactors in AVS in the US. Said lead reactor is the safest, and LINA, the classification organization in Italy, said lead reactor is the safest because it is the most economical because it doesn't require any replacement for over 40 years. And it was already used for the Soviet Union's nuclear submarines, and lead can be sunk down to the bottom of the sea. And Norwegian Science Technology University collaborated with DMV, said sealer is the safest. So lead fast reactor is getting more popular because it can ensure safety, not only offshore but onshore. Last May, LFR, manufactured by Nucleo, was discussed at this negotiating table attended by French president, and the French president said France will build LFR plants. France has been strongly pushing forward LFR. It has the most advanced technologies when it comes to sodium, but since the Fukushima nuclear leakage accident, they have been staying away from LFR. They have been staying away from nuclear power plants, but this time they decided to build more LFR power plants. For the shipbuilding and shipping industries, natural circulation, LFR, and the whole life cycle can be covered by LFR. So it is a prevailing thought that LFR is the best alternative and solution. There are three technologies that are competing. One is nuclear, co-developed by Italy and the UK and chosen by President Macron. The second thing is solar. And MicroURANUS, which is a Korean one that is under development by cooperation between Korea and Norwegian company and Lloyd. These three technologies are competing in the market. Nuclear offers 15 to 20 years of lifetime, solar 30 years, and MicroURANUS 40 years, the longest. That is why Norwegian group and Lloyd proposed cooperation. This technology has been developed by Seoul National University for the past 30 years, and UNIS and KAIST and SNU work together to refine this technology over the past 10 years. And specifically, in the last 4 years, the endeavor had accelerated, and within the units we will build a lab for further facilitating this endeavor. It is 11-meter high, and this reactor can be mounted on a large container ships, and it is without any risk of meltdown. Under the worst case scenario, radioactivity will not be leaked outside the reactor, so it doesn't require any emergency evacuation. So compared to the other two LFR, this one is most competitive and safest. I don't have much time left, so I'd like to conclude my presentation by showing you this video. So please click the play button down here. This microreactor can be manufactured at a plant, and nuclear power can be fueled here, and pilot tests can be done at the plant level as well. And it can be loaded on a truck, and the truck goes to a harbor. And here we are using plug-and-play system. Once it is mounted or fuel a ship, the ship doesn't need to refuel itself for the next or for the following 40 years. And calibration operation can be remotely controlled or remotely done once every 2 years. And once the fuel is filled, it will be welded, so there is no risk of liquids. So it is safe in terms of security as well. Once it is decommissioned, once the ship is decommissioned, the fuel can be recycled. So highly active waste will be disposed, and medium level waste will be taken to Gyeongju treatment facility.